Okay, it's 8 a.m. Pacific time. Let's get started. So I'm Wei Xiao from ARM Machine Learning Ecosystem. I will be the moderator for this session. Our speaker today is Jongboom from ARM.
Hey, Wei, thanks so much.
Hi. His topic is efficient machine learning across ARM from Cortex-M to WebAssembly. So Yang worked for ARM until last year. He then co-founded Edge Impulse to bridge gaps in machine learning development. Yang, do you want to introduce yourself and talk about your business adventure?
Absolutely. Thanks so much, Wei. Hi, my name is Jongboom. I'm out of Amsterdam. And you might think, okay, well, it's August 25th. Why is Jan sitting in a dark room? And that is because the weather here thinks it's autumn already instead of still summer. But yeah, wonderful. Thanks so much for the introduction, Wei. Like as said, I worked at ARM for 3.5 years. I was leading the developer evangelism team at ARM, and as part of the projects that we ran there, we also had a forward-looking project with Embed Labs, where we were looking at how do we think that embedded developers are writing software 5 to 10 years from now. And for us, 2 or 3 years ago already, we saw kind of this trend where devices get more and more capable. There are more and more devices being shipped every year. I think the last figures I saw was 22 billion ARM processors every year. It's an astonishing amount. And these processors don't go in your desktop computer or even in the little supercomputer in your pocket with your mobile phone, but rather in everyday objects, maybe in my piano here on the right, or in industrial machines. The very, very wide variety of chips is going in there. So we have this amazingly capable chips. If you look at what a Cortex-M4F these days can do in terms of raw compute, it's actually astonishing looking at the power profile. And there's a lot of them, an insane amount. But if you then think of what we actually do with those devices, it's often very little. We take a device, we read a temperature value, and then we send that temperature value to the cloud. That's kind of it. Mostly because these devices are bound by either by power constraints. So you just can't send data very often because then you drain the battery really quickly. It might be that sending data to the network is actually really expensive because you need to pay your telco maybe. Or maybe it's just too hard to do all the pre-processing on the edge, and you much rather do that somewhere in a central location, but it limits the amount of data that you can actually send through. So my team at ARM, but also the ecosystem team and the wider team in kind of the team that now is doing new architectures like the ARM ethos architecture, kind of saw the need for putting some local processing power on these chips and building an ecosystem around it. So my team at ARM started a project called Microtensor. Neil Tan here on my left was leading that out of my team. That eventually got merged into TensorFlow Lite for microcontrollers. And when that hit back in May 2019, like this machine learning on embedded systems really, really took off. And I think it's a fantastic show here that we actually have an AI Virtual Tech Talk series now as part of the ARM domain, but there's a very wide variety of companies, not just ARM and not just my company Edge Impulse, but a very wide variety of other companies also jumping on that ship and showing that building embedded devices with true intelligence is really possible and really going there. So that's what I want to talk to you about today. A bit about the background, like where do we come from? We've been doing this embedded ML for a long time, but we're finally getting to a stage where we can actually deploy this in the real world, because it's not as easy as just making some silicon that can run neural networks fast, or just having a machine learning model and running a TensorFlow Lite compiler and then getting something that you can run on device. But it's much wider, like how do you actually do data acquisition? Where does signal processing still fit in, and going from there. Then I also want to talk a bit about like where can you deploy these things. We've been talking at least in this talk series a lot about how can you make these models run on device, but this might not always be the best deployment location at the very first time. We still have gateways that are being around, and it's very often much easier to deploy a new application on a gateway than to completely put a new SKU in the market, because that might take 1.5 years or 2 years if you actually want to run the software on device. And there's even a place, I think, for machine learning on sensor data in the cloud. So we'll look a bit about all those deployment options in the next time. So yeah, a short recap. If you've been watching this video series over the last months, this should be familiar to you, but I think there's some things that are really easy currently if you're building connected devices or if you're building embedded devices that need to take data from the real world and then do something with that. For example, getting the temperature is trivial. And that's probably why the very first circuit that you've ever built was a temperature reading measurement system. And why kind of every IoT project starts with, here is how you send the temperature data to the cloud. Because, well, for temperature data, I can just buy a sensor. This is a digital temperature sensor, but you also have analog thermistors, which are not as precise, but are really, really easy. You just read the voltage that goes through them, and they adjust the resistance based on the temperature. So you get a value out. So here, maybe minus 10 degrees Celsius, and then you send it to a cloud, and bam, you can do that in 20 lines of code. Some things used to be, if you look back 20 years ago, used to be incredibly hard, like positioning of something in physical space. These days, you just buy a GPS chip, you slam it on your design, and it just magically works. Now, naturally, this is not, it's still a very hard problem. But a lot of really smart people in the wider industry have thought about it. We've launched a bunch of satellite constellations. We've worked really hard in making the chip smaller and smaller. Here's a nice one from uBlocks, but there's a wide variety of vendors that do this, either on GPS or in Galileo. And now, as an industry, you made this really, really easy positioning. Still constraints, but a lot easier. Some things, though, are still hard. And that's because I can't buy a sensor for it. It doesn't have to be hard for a very long time, but it's something that's still hard at this point. Like, do I hear glass breaking? I can buy a MEMS microphone, and you have super nice ones for like under $1, and I can measure like the loudness of things that I hear quite easily because I get data in PCM signal, and I just look at the volume. But detecting from all the possible sounds that I hear on an average day, and then distinguishing glass breaking is a really, really hard task because there's an insane amount of data points. Even if I'm looking at, you know, even relatively low resolution audio data, we're looking at 16,000 data points a second that we then need to analyze and compare. Really hard. Some other things that are also hard. Some other things that are hard is if I have a complete fleet of machines and I stick an accelerometer on it, which we've been doing for predictive maintenance for a while already, it's relatively easy to detect like when a big shock is being heard. So often at trade shows, Hannover Messe, like the big industry 4.0 trade shows, you'll see a machine, there's a sensor being stuck on it, and then someone slams on the machine and a signal is being recorded that something is amiss. Great, easy use case. But you can do that because you can just measure the peak motion that you see on the accelerometer. It's much harder to look at questions like, is this machine doing something differently than all the other machines in the factory? And can you explain that because the positioning of the machine or the floor is a little bit different, there's other machines oscillating there as well, and you see some of that resonating to the machine that you have there. So how do you see that a machine is vibrating differently, and can you act upon that? Still really hard. But we're making progress really, really fast as the industry, which I think is showing here in this talk series, but also in like the sheer amount of research that is coming out around machine learning. This is an XKCD back in 2014, where they kind of ask like, okay, when I take a photo, I should check whether I'm in a national park. That's great. Now I have a GPS chip and I do a lookup and I see if I'm in a national park really quickly. And then I want to know if the photo is of a bird. And 6 years ago, this was kind of, we knew that it might be possible to use machine learning to do these kind of things, but we knew that we still needed large clusters of computers for it. These days, it is, but it's not trivial, but it's getting a lot easier to solve these kinds of problems. And that is not because our computers get faster and faster. No, it's because there's a whole bunch of researchers and a whole bunch of computer scientists putting real effort into that. So I think for like the really hard tasks that we still have, here my examples are glass breaking and machines oscillating a little bit differently, are hard, but getting easier and easier once we understand kind of this idea of machine learning better and where it's useful for and what we can use it actually to deploy. So for me, kind of everything right now where we need to find patterns in really, really messy data. So that can be photos, because visual information is really hard to process. As humans, we do this really kind of naturally, but for machines, really, really hard to distinguish between things. Doing stuff with audio data, or stuff where you have lots of machines feeding data into the same model. Like if I have one machine and I want to detect if I see something like here, okay, great, I do an FFT on basically accelerometer data, and I see, okay, well, do I see like a little bit oscillating differently on my thing? Relatively easy to do. If I now need to do this over the million machines that I have all over the world, getting a lot harder just because there's a lot more messy data. So yeah, machine learning for a long time was just associated with these large clusters of computers sitting in a data center. I remember when I saw AlphaGo beating the best human Go player, I was absolutely astonished that a machine learning algorithm could do that. But Google actually developed their own custom processor just to train that model, the TPU, which is absolutely brilliant, but completely out of scope for me as an ordinary developer, especially if I also want to move that to the edge at some point. Fortunately, this kind of movement was led by two super smart people that kind of had a similar idea at the same time. So Pete Warden, who was working at Google at the time after his company was being acquired, and Neil Tan, who was working at ARM, who was actually a marketing engineer at that point, looking at like cool stuff to do with embedded systems. And they both figured, if we want to run these machine learning models on device, which is super useful because now we can start doing some of these analytics straight there, even when I have these constraints on bandwidth or power. If we just focus on the inferencing part, so just on, I have a model and now I ask the model what is going on, these models get a lot smaller and the compute load gets a lot smaller. And that is because a machine learning model, in essence, is just a mathematical function with a lot of parameters. And this might be 100,000 of these parameters, or even more if you looked at vision models. And getting the right value for all of these parameters is a really complex and hard process that you want to do on a cluster of GPUs. But once you figure out the mathematical function, then running this on end devices is actually very doable. Like a Cortex-M4F these days runs at 80 megahertz, is capable of doing 40 million IOPS, or maybe even 80 million IOPS a second, and doing a bunch of vector multiplications, which is in essence what is happening in that mathematical function, is something we do on a daily basis. So once they kind of proven their first premise, the wider community kicked in, and we really had this kind of TinyML movement where people realized, okay, well, this mathematical function, we don't need that much accuracy while we're doing this inferencing step. So can we reduce the accuracy within the model? Great. Can we reduce the number of parameters? Are there parameters that actually don't contribute much to the results? Great. Can we find out about those? Fantastic. Then a lot of work that ARM has been doing is, well, we have vector extensions on an M4 or an M7, and a lot of these things are vector operations. So can we leverage those to actually use hardware optimized paths? So CMSysNN and in a way also CMSys DSP, which we use for a lot of our signal processing handling, really make this really fast. They're kind of automatically vectorizing these things like multiplication, which is things we do very often in these models, make it much, much faster. And from there, yeah, we're basically leveraging silicon, and silicon is already good at doing doing mathematics, so we can go really, really fast. So for silicon, we can either do specialized silicon. You see a bunch of companies now shipping their own neural network coprocessors. So they've laid these kind of mathematical functions already out in hardware. They ship with separate signal processing blocks in there, or what ARM is doing with the general purpose processing or vector extensions going forward. For me, kind of the big revelation here is that this allows you to do really wide deployment options. It's not just, if I have a model that can run on the sensor, that means it can also run on a gateway because it's probably more powerful than my sensor. And if I have something that runs on a gateway, I can also deploy it in the clouds because that is even more powerful. And that gives me a super flexible deployment mechanism because I don't want to replace all the sensors that I have in the field. And if I want to convince one of my customers to actually run a trial, I don't want to ship them new hardware. Much rather, I just hook into the data stream that they already have, where data comes from their sensors into the gateway, and can I throw some data in there, or the initial validation in the cloud. So for me, if you just start building with edge devices in mind, you kind of never locked out. So yeah, if you want to do it in the cloud, fantastic. It's super easy to do compute. It's really easy to deploy. The compute is relatively cheap. It's really expensive to get raw data there because, if you think about audio data, sending 16 kilohertz of data points every second from an embedded device, that racks up quite a bit of a bill on your device, and maybe it's even too expensive on your power budgets. On gateways, easy to retrofit. Lots of gateway manufacturers are moving to a model where they allow you to run something on their gateways because they see they have lots of excess compute. So easy to retrofit, especially if you already have the raw data stream. So rather than a signal processing output, like an FFT output, if you already have the raw data stream, relatively easy to get something in. And then naturally, the edge device will give you the best, potentially best performance because you don't involve the network anymore. So your latency drops. It gives you potentially the best power consumption budget because you don't need to drive the radio, which is often the thing that sucks the most energy out of a battery. But yeah, it requires new firmware and planning, and we all know that is going to take a very, very long time. Potentially, you could do a hybrid thing here, right? The edge device could do the signal processing step. The gateway could do a first pass on the ML part, and when it sees that something is amiss, like they see an anomaly, then they send the raw data to the cloud to collect some data. So let's kind of go from zero to model and see what we can build and deploy and where our pain points are. I'm still a little bit surprised that I need to say this, but I've been in the field a little bit too long. Everything starts with raw data. When we talk to customers, even customers that know that data is kind of their bread and butter and the thing that differentiates themselves, they very often don't have raw data at the highest resolution possible. Even predictive maintenance companies that we talk to, they have the result of their signal processing steps, maybe the result of FFTs, but not raw data. But for us, for any machine learning purpose, it's much easier if you have this data at the highest resolution possible. Even if you're not going to use it at the resolution, try and capture it. Even start doing this 3 to 6 months ahead before you even know what you want to use this for. If you have raw labeled data, you're going to make your life a lot easier and make the validation of if you can do something with ML. If you can do something with ML actually feasible. Second step, it's not that we haven't been doing analytics on device. We have, but we just call it signal processing. And I still believe that we should not throw away like the common knowledge of what we've been doing as an industry for the last 30, 40 years on processing sensor information and throw that kind of away. And I also don't think that machine learning is this magic black box where you put data in and at the end a model pops out and that's what I want to ship on my devices. Because I'd like to explain what my model is doing. Doing an initial pass on extracting meaningful features that I know are relevant for my data, just because I have proven DSP algorithms that do this, like an FFT over anything that rotates, or calculating ML frequency capsule coefficients over anything that has to do with audio, is great because I reduce the feature space. I go from, let's say, 16,000 data points on audio data to maybe 300 that I have on a spectrogram. And I can explain this much better because if my customer comes with a bug and says, well, your fantastic new machine learning model is great, but we have this anomaly, we have something that doesn't work. Being able to go into the model and determine what is going on is a lot easier if you did this first pass on extracting meaningful features. So yeah, like I'll show it in the demo as well, but an example of a signal processing pipeline can be done where I take my input signal, like saying yes, just calculate the speech features here by doing an MFEC spectrogram. And here we just reduce the number of data points from 32,000 bytes, 16 kilohertz times in 16, to 240 bytes, making it a lot easier to distinguish the data. Similar for anything that rotates, or anything that has to do with accelerometer data. Here's me doing 3 different movements. One is moving up and down, the other one is doing a fist bump, and the last one is drinking a beer. If I just look at the raw data, I can kind of distinguish the 3 different motions. You know, I see that a fist bump has some energy in the middle, and up and down has some energy up and down. But if I look at any of these single data points, I can't distinguish what it has to be. So it needs to be some extra calculations. It's pretty noisy. If I just do a fast Fourier transform over the data and look at the height of the first peak on the X, Y, and Z axes, bam, I can just plot this data straight away. And I barely need any machine learning. So that is actually a good stop point here as well. If you can do it without ML, definitely do it without. But, yeah. And from there, let the computers figure it out, right? I kind of distinguish stuff between classification issues, like what is happening right now. Anomaly detection is what I'm seeing out of the ordinary, or forecasting, like I have something and what is going to happen in the future. Neural networks get all the hype these days. If you look at the development, like what ARM is doing with CMSSNN, lots of these focus is, it's even in the name, neural networks. But neural networks are definitely not always the right algorithm to go with. They're great, but they're also kind of magical. And this whole idea of like explainable machine learning, which I like to do at least when I deploy something into the fields, means that for me, using something, maybe a classic ML algorithm that is much easier to explain, like k-means clustering, doesn't have to ring a bell, I'll show a demo of this later, might actually be a much better choice because it's much easier to show what is going on and why that might not be the case. For really high resolution data, like audio data, it's kind of your only way out. But if you do something on a lower resolution, definitely also look at some other things. But yeah, for example, we use anomaly detection. We don't use neural networks for it, but rather we train and we learn the clusters of data that are there. Those clusters are explainable. I can just draw them here on a 2D canvas. And then when new data comes in, I can compare the data to a cluster. This is data after a signal processing step. And when it's too far out of a cluster, I know that it's an anomaly. Much, much easier to explain. And then finally deploying this. So take your signal processing code, take your neural networks, take your anomaly detection code, take any other ML algorithms, and deploy it as C++. There's been some really great work, one by ARM, by Google, by ST, and well, also by Edge Impulse, in making this kind of stuff easy. So if you have a machine learning model, how do you go from that trained model to something you can run efficiently on device? So tools like TensorFlow Lite, STM32Cube AI work really well for that. And then you can make your signal processing faster with things like CMSS DSP. Here, take advantage of the hardware as well. I think the cool part here, we'll show it in the demo, is that if you write everything in C++, because you're going to go deploy on edge device anyway, for your gateway and cloud deployment, you get this extra deployment option of taking your whole C++ library, cross-compiling it to WebAssembly, and then you can run this on your gateway, on your cloud, or even in a browser in a JavaScript runtime like Node.js, which gives you this isolation of your ML model without even the VM and without any of the installation struggles that you might have. Rather, up to your customer, you just say, okay, here's a Node.js application. Everyone knows how to run that anyway. And it doesn't need any special permissions, no compilation toolchain required anymore. So it's trivial to deploy. And very often, if you already target something that needs to run on an edge device, it's gonna run on the gateway even without using any of the hardware optimized paths. If you're deploying on a Cortex-M that has an FPU, like in Cortex-M4F or Cortex-M7, use CMSS DSP and CMSSNN to leverage those vector extensions. There's tools that do this automatically, like all this DSP code that Edge Impulse spits out and all the machine learning code that we spit out uses automatically already. Similarly, if you use TensorFlow Lite with CMSSNN, this will use that as well. So that makes it kind of fast out of the box. And then if you use Cortex-M with a neural network engine or with an external DSP, like Compute has their Compute ECM3532 that ships with an M3 as a general purpose compute unit. And then they ship with a CoolFlex DSP, 16-bit, that you can offload these operations to. And very often these vendors already ship with a library that allows you to just compile your application and run it there. But a bit less easy to do generically. Kind of from there, your models are kind of driven by your silicon capabilities. So it's not an absolute truth here, but how I kind of see it, like if you have a Cortex-M0 Plus, you can do anything with vibration and accelerometer classification. You can do anomaly detection on those and even basic classification. If you have an M4F, you can do real-time audio. That can either be continuous things like scene detection, like am I currently in a train, or do I hear a TV playing in the background? Or it can be discrete events like a keyword or glass breaking. Once you move up to a Cortex-M7, you start being able to do basic image classification. So on the OpenMV cam that I have laying here, which is a Cortex-M7, we can do 10 frames a second at 96 by 96 pixels, which is pretty cool, doing full image classification. Then if you go to Cortex-A class, you start being able to do object detection. So I have multiple things in my video frame. Do I see two people and where are they in my video frame? Whereas the image classification you do on M7 is more, do I see a plane or do I see a person, or is the label on my bottle placed correctly? And naturally, if you go to cloud, you can kind of do anything as long as you want to pay for a cluster of GPUs. Co-processors can offset this a little bit. I'm super excited about what ARM is going to do with the Ethos silicon, because that allows you to run even more stuff, even on most of the basic microcontrollers. So getting started, we'll do a demo of this as well. What we do with Edge Impulse is after my team at ARM built or helped to build and mainline TensorFlow Lite for microcontrollers, we figured, okay, cool, now we have an inferencing engine for neural networks, but no one can actually build these models because you need someone that is both a data scientist, an expert embedded developer, someone who knows a lot about signal processing, and someone that knows how to optimize these models to run on real hardware with the constraints that you actually have there. So after we left, both me and also my co-founder Zach was at ARM, we figured, okay, let's build everything else around it. So how do you actually do data collection from real devices? How do you, what we think signal processing is useful. What are the signal processing algorithms that are going to be useful, and how do you expose that in a nice manner? Then build a machine learning model from there, and then finally deploy that back to device and all this management around it, because building this data setup is super valuable IPR for you, and something that if you spend some time and money on, can be a competitive advantage, which we actually see for some of our customers. So we partnered with a bunch of silicon vendors in actually enabling this full tool chain. So if you want to, after this webinar, you're interested and you want to start building your first ML algorithm that runs on device, grab either the STI Discovery Kit, the Arduino Nano 33BLE Sense, the Edicompute AI sensor, or the OpenMV Chem H7 Plus. The latter is one that can actually do video and image classification as well, so that's super cool, has a camera on it. Or, as I said earlier, if you build everything in C++, then you have this deployment option of doing things in WebAssembly in the end, because you can turn C++ compile it with Mscripton, and they get a WebAssembly blob. And WebAssembly runs in any browser or in any runtime environment where you can run JavaScript, including your smartphone. So the full pipeline from data collection all the way to actually running the trained models can be done completely in the browser, no app required. So you can get started building vibration models, anomaly detection models, audio models, and even vision models straight from your smartphone. So really easy to get started. Yeah, and then Edge Impulse is there as kind of this TinyML as a service. Everything is cloud-based. It's completely free for developers. We spit out code that you run on your devices that is open source license, royalty free. So once you created your model and you deploy it to device, we are out of the loop. But we help you build this complete kind of pipeline of machine learning in there. And we have excellent tutorials on vibration, audio, and vision at docs.edgeimpulse.com. But what good is just talking about that if I can also show you? So now I want to head over to, first I want to have a little Q&A section of Wei. Is there anything that we got from the audience?
Yeah, sure. We received some questions from the audience. And if anybody else has any other questions, please use the Q&A window to raise your question. So very nice question from our audience. We all know that memory management is very important for TinyML development. So will I be able to enable other stacks like Wi-Fi, BLE, and not running out of memory on the devices?
Oh yeah, that's a really good question. So yes, okay. Naturally, there's not one answer, right? Because on every embedded device is a little bit different, and we have different profiles. What we can do actually, so this is a Cortex-M4F from ST, has 128K of RAM. It has an external Wi-Fi radio, so the Wi-Fi stack is not on here, but kind of the IP stack is. And we can run both data collection, running machine learning model, even audio models in real time, keeping a Wi-Fi connection open to do extra management, and even running our TLS library to sign new samples, all in 128K. We provide some guidance, I'll show it in the demo, on how big your model is. And we don't have it right now, but we're working on a version of our SDK where everything is statically allocated, so you know exactly like how much memory you need on device and how much you have left for the rest of your application.
Cool. Another question. You mentioned the TensorFlow Lite Micro. We know that you support ST's Cube AI as one of the inference engines as well. What other frameworks do you support? Do you support custom inference engine?
So we custom inferencing engine, we mostly use stuff that we get from vendors. So this is a little dev board from Compute. So that is a Cortex-M3 with an external DSP on it. And they provide a tool that takes a trained neural network and then cross-compiles it into optimized instructions that can run on the DSP to make that stuff fast. And I expect us to keep adding more and more of these things once more silicon comes available that does this efficiently. So yeah, we're pretty open in what we need to use. We're working on, besides TF Lite and QPI, we're working on kind of our own version of a compiled version of TF Lite, so you don't need the interpreter, which is going to save a little bit. But yeah, we're taking it depending on the silicon capabilities.
Cool. Next question. What's Edge Impulse business model?
Yeah, so we're free for developers. We get paid some money from the silicon vendors to offset the cost for the free developers. And then we have an enterprise plan that helps customers build kind of this really valuable data set that is worth money. That is actually, really valuable IP that you can build. So we work with, we have a couple of large customers that pay the bills there. So that's our business model.
Okay. You also mentioned Ethos. So for the Ethos U micro NPU, is Edge Impulse going to provide integration once the silicon is ready?
Yeah, absolutely. It naturally depends a little bit on like what the community wants and what our silicon partners ship out. But for us, it's always like, if we know a way of making this stuff run even faster on commodity hardware, then yeah, absolutely. That's something that we'll do. Should we add to demo? And then we'll do another round of Q&A right after.
Question. Oh, do you want to address one more question? How about support for 2 cores like M7 plus M4?
That is really interesting. I haven't really given it much thought. So a little bit. So we use this not with 2 cores, but at least with 2 threads for stuff like continuous audio classification, where we can use one of the cores to do continuous sampling of the audio, running a DSP algorithm on 1 core, and then running the actual classification on the 2nd core. And that way we can run a bit faster. It's, however, really, really hard to write code in a generic fashion to kind of do that and take advantage of this automatically. We do it a little bit, for example, in Compute, where we run some of our main calculations, anything we can't offload to the DSP on the main MCU and then offload to the DSP. But it's still like a handoff, and then we get back. But we can voltage shift the CPU down to reduce the power consumption. But kind of what we give you after you export the model is just source code. There's not a single compiled library in there. Everything is royalty free. So take our DSP codes, take the things that we use to invoke our neural networks, and you know, mix and match it with how you want to use it. And if you want to offload some stuff to one CPU and some stuff to the other CPU, feel free. We don't stop you there. And unlike some of the other vendors, we don't ship binaries.
Thanks, yeah.
Right, cool. Yeah, let's switch to demo here. So let's open my phone here as well. So yeah, Edge Impulse, it's free. You can just sign up, edgeimpulse.com, click the sign up now button, fill your name, and go. And from there, you can start building a project. And for us, kind of a project is a flow where we start with real data from real devices, because that is literally it's fun if you want to train a machine learning model and someone says, okay, here's the data set. And here's the machine learning model architecture, press this button, and now you have a trained model. That's not fun for anyone. So for us, we try to make the experience really nice where you can actually go collect data from real devices and then build your own model specialized with that data and then deploy it back to that device as well to give like a really, really good interactive experience. So I'll show three small projects here, one around vibration data, one around audio data, and one about image data. And I'll have it running on a variety of devices here as well. So on my desk, I have the STIT Discovery Kit. It's a nice kit. I said 80 megahertz processor, 128K of RAM, and it's connected here. And if you have one of these kits, so this can be the 5 dev boards or the 4 dev boards that I showed in the presentation, or either your mobile phone, you can go to data acquisition and just capture data straight from the device while it's sitting here. So if I want to build a gesture detection model, something that can detect whether I'm waving or moving the device up and down, I can just start capturing data. I select the sensor. This one is an accelerometer and a microphone, and the frequency that I want to capture data at. Click start sampling. I just move my device. Now we sample on device, then we sign the data, and then we send the data back over. So there we go. Beautiful. So that's me doing a little bit of waving. If at some point I think, okay, well, I took a little bit too much, so just say, okay, crop sample, great, bam, and done with it. So I've done that. I built a collection here of 15 minutes worth of data over those 4 classes. So I have wave, about 6 minutes of wave data, 3 minutes of idle data. That's just me sitting on my desk. 3 minutes of snake data, or just moving left and right over my desk. And the last one is 3 minutes of up and down data. So what I said in the presentation is my very first step, I think, here is how would you approach this if you didn't have any machine learning at your disposal? And naturally, if we look at the data here, it's a continuous pattern, right? Because I'm waving and I'm looking at kind of this continuous motion that I want to classify, and that is visible here as well on like up-down movement. If I have any continuous motion, the very first step that I would do on device would be say, well, then I want to look at the spectral features here. I want to run an FFT over this data and then look at the heights of the peaks and the power spectral density of this data to look over it. So we have a bunch of blocks built in Edge Impulse that take kind of these best practices in signal processing and allow you to apply it to your data. So spectral analysis, image pre-processing, audio data based on mel frequency, central coefficients, or if you already have something, you just click the add custom block and there's a tutorial there to plug that in. And then from there, I want to have a learning block. So it can be a neural network if you want to do some classification, but we also do non-neural networks. So I also like to deploy an anomaly detection block to know when something is really, really weird, when something else is going on except for idle, snake, up, down, or wave. And then finally, I have 5 output features, which are my 4 classes and an anomaly score. So this gives me my, my spectral features block. Here I can say stuff, okay, well, I want to apply a filter to denoise the data, standard signal processing step. If I switch to a high pass filter, then naturally only my noise is retained, which is not that useful. With the cutoff frequency, I can set the filter order. I can set my FFT length, the number of peaks that I'm interested in. So here, 3 peaks are is kind of okay. And my power spectral density power edges. So very similar to what you'd be doing normally on the signal when you look at signal processing. So with that, I can generate my features. My data separates nicely as well. This is just looking at the RMS. So the kind of the average total amount of energy in the signal on the 3 axes. So it looks good. From there, I can train a neural network. We populate this automatically with something we think is going to work. I'm blazing through this a little fast because I want to go through the other 2 models as well. After that, we can see our training performance. We'll see our confusion matrix. So sometimes there's a little bit of confusion between up, down, and wave, but not too bad. And we can show our on-device performance. So we can automatically load optimizations, like doing quantization of your neural networks to make this run faster. And we give you an indication of how much memory we think we're going to be using. From there, I can also go add a second block. So here I have an anomaly detection block where I take the RMS data, learn the clusters, and then I have another trained model that I can then use to do an anomaly detection. So let's actually see if this model works. So I'll get some data, move my device up and down. So that classified as up down 16 times, which is great. That is exactly what we're doing. So we think this model might work. If I start doing something really weird, like shaking my device, this is the most fun part of my demo. We actually see that we think this was anomaly quite often. You see some data here, but we also see a couple of places where it looks a little bit too much like wave. So this might be a sample where we need some additional data, or there's some data in our data sets that is too close to this. So we see some data here, so I can click on it. And apparently some of the features that were generated from here look too much about the shaking that I just did. So this might be something where I want to get rid of this data in my training set, or change my anomaly parameters a little bit. So you see that they're very close to 0.3. So in this case, maybe my cutoff date should be like 0.25 or something. So we try to help you guide a little bit in when a model makes a wrong decision, why it's doing that, and it allows you to learn from that. And we try to do that with visualizations, showing which samples are closest based on the parameters that you're looking at, etc. So cool. Okay, so that's one model. I'll show some stuff running on the device with the other ones, but you can go to the deployment tab, select either the library or a CMSIS pack or one of the boards for the dev board, and then run it straight on device. Or as a WebAssembly blob if you want to run this, for example, in a gateway or in your browser. But I'll show that on the audio and the vision models. So for audio and vision models, we have the experience is very similar. So once again, we start with devices that collect. We can then get data. I'll actually do some data from my mobile phone now. So I'll have my phone here. And I'll show you how easy that is. So I say use my mobile phone. There we go. Jan's iPhone is now connected. And what we have here is a keyword spotting model where I distinguish between 3 classes, which is Jan, my own name, noise, which is just background noise, TV playing, static noise, etc., and then unknown, and these are other words. Let's see if you can actually hear this. Okay. No, you can't hear that because it's routed to my microphone, to my headset. But let's collect some more data from my phone now. Say Jan, 5 seconds. Give access to the microphone. Jan, Jan, Jan. Oh, this doesn't play for some reason on the thing, but here's the data. Now, naturally, these are discrete events. So I want to split this data first. So I click split data. It automatically gets the 3 samples that I have. I can click on it and listen to it if needed. Split it, and bam, now I have some data. We automatically shift it a little bit in the window to go from it. And then from there, I need to get my... see if we can get my phone back here. From there, we have a similar pipeline. So instead of the spectral analysis feature, we now use an audio block using MFVC to get this data in, and then use a neural network classifier block to classify that data. And here, rather than a fully connected network as we used before, we use a convolutional network to kind of train. And once again, we get like pretty good accuracy going from here. Now let's actually, if I want to run this on device and see how that actually works there, I just hit the SDIT discovery kit, the board that I have laying here. I can analyze some of the optimizations. So we can reduce the accuracy in a network, but that also might mean that we lose some accuracy. So we can do that here, but let's keep it now. Just hit the button. We compile this for you in the cloud, and then deliver the binary file to you. So I've done it already prior to this, just for speed. So I'll cancel that. So I have the little dev board here, running that same model. And I can open my window and then run edge impulse, run impulse continuous. At that point, we run in a continuous mode. So as I said in the Q&A, for some stuff, we analyzing like a full second worth of data is like 400 milliseconds. So we can only do it like twice a second and we still miss some data. So here we kind of continuously feed data into the DSP algorithm. And then whenever we have a full second worth of DSP data, then we run the classifier. So that makes this run in real time, even on an M4F. Just stop my dev board here. So running here, pretty easy. And now I say, yum, and I heard my keyword. So, yum, so brilliant. So super easy, you can build your model on real device, get some data from real device, and then finally deploy that here. And we make it really easy and really fast to kind of run this. Now, I hope that my phone gets back here, so I can show this running on phone as well. Give it one more try, and otherwise, you also believe me in my blue eyes. On iPhone, okay, there we go again. So if let's actually show that with devices. So when I hit switch to classification mode, we now build the WebAssembly binary and then ship that off to the device. So, okay, and I think that's the problem. It doesn't allow me to share my screen whenever I'm also using a microphone. But we ship a WebAssembly blob to the phone. And at that point, the phone will just run this ML model straight from the browser, which is super cool because now you can just see what is happening here, going literally from your phone, running this whole model there. But yeah, try that out yourself. So the last thing that I want to show here, and then we'll head to our Q&A, is that we can also do things around vision. So an M7 and up these days is actually fast enough to run computer vision models. Gateways definitely are fast enough, whether you run it at WebAssembly or just run native code. So we've been adding a bunch of features here, similarly to how you can currently do a recording of data from your phone or from a dev board. You can also get data from a camera, like the OpenMV cam, or just import a bunch of JPEG files. So what I trained earlier today is a small model that can distinguish between my piano and my lamp, which is there on my right side, and then also between a plant that I have here, and then some unknown data. So as you can see, very little data actually. So this is just 4 classes, 126 items, and then some data in a test set. To make training this faster, we've added transfer learning, which allow you to use a base model, and then strip the top layers of the base model off and only retrain those. Now the neural network is forced to learn kind of basic stuff like shapes and contrast in the lower layers, and this generalize pretty well. So we look at actual model testing performance in the real world. So this is on a test set that the model has never seen. Here about 86%, it's pretty decent. And when I want to deploy this to the OpenMV cam, I just hit the library, hit build, then I get a zip file, and that's something I can run here. I've done that for you as well. So let's click the connect button. And at the bottom of the screen, you're going to be able to see what the camera is currently. So here you see what the camera is seeing on the right top corner. So right now it's seeing my ceiling. And here at the bottom, you'll see like what the model is looking at. So when I pointed at my lamp, now we see a lamp. When I pointed at the piano, it's pointing at the piano, and when it's pointing at me, fortunately that is unknown again. You'll never know when this classifies as a plan. So super cool, running in real time, 4 frames a second on this board. Once we get the CM2ZN integration, this will be even faster. So cool. So I want to do a quick recap. Everything you've seen so far today is open for you. You can just go, sign up, start building it. Only thing you need is your phone or one of the dev boards that is supported. And for me, being in the space for 2.5 years and seeing how fast we go as an industry, I really have to say the ML hype is absolutely real. We can really go from raw data, raw sensor data, to working models that perform really well in the real world and run in real time on our edge devices. And that is no longer just a pipe dream, that is something that's really here. If you think, okay, well, this is great, but it can't actually replace my devices, this stuff is fast enough to also run on our gateways and in our cloud. So design for edge, that means that you're never locked out. You can deploy this anywhere. So this machine learning thing is absolutely real. Also, machine learning and sensors are a perfect fit. We have lots of underutilized sensors laying around, whether it's microphones, accelerometers that just measure the peak motion that they see rather than actually classifying what they do. And just because there's so much of this data, the only way to unlock this is actually put ML closer to the sensor. I think it's a really perfect fit with how well they are. And last thing, like start doing the impossible. Like 20 years ago, we thought that in the positioning on small battery powered devices would be really, really, really hard. 6 years ago, we thought that classifying what we saw was really, really, really hard. And now we see that these things are no longer impossible and are doable even on the smallest of devices. So start doing the impossible. And if you do, please head to edgeimpulse.com and sign up and start building. And then I headed over to Wei to talk about the next talks in this series.
So Yang, thank you very much for the next demo. I have to say you look like a ninja when you were collecting sensor data. Cool, some questions from our audience. How much data do I need to train a model?
It depends a bit. More is always better. But we typically see, typically you can already validate if your model performs well with about, for accelerometer projects, maybe 15 minutes of raw sensor data. Raw sensor data at a high resolution. For audio, about half an hour to an hour, depending on your use case. Continuous, like scene recognition is a lot easier. And for images, you can, thanks to transfer learning, actually do a pretty good job with about 100 images and just get a general sense of whether ML can learn from this. And then from there, you know, more data is always better. Cool.
So what sample rates does your toolset support for various sensor types?
So what's, sorry?
What sampling rate does your toolset support? Yeah.
It all depends on the sensor. So we don't really care. Like we have accelerometers at 8,000 hertz. We have audio at 44,000 hertz sampling in. The only thing that we say is give us data in this format and tell us what the frequency is. And then we'll deal with it from there. So kind of anything from 50 to 20,000 hertz will work. But the higher, the better. That's
okay. So related to data collection, so you mentioned that the more the better, but you also need to be able to collect and ingest massive amounts of data to create a reliable and a deployable model. So how does edgeimpulse support that?
Yeah, so our basic acquisition tools make it really easy to get some data from like these devices, but naturally that is not the flow that you're going to be using if you're building, if you have lots of devices in the field. So we have a couple of tools that help with that. One, we have an ingestion API where you can just send data to. So if you already have data sitting somewhere and you just wanna get that in, you can use that. And then in our enterprise version of the product, we have tools to do massive data engineering. So we have tools, stuff like, okay, well now I want to do feature engineering on 40,000 people to detect sickness, which is very relevant in today's climate. We have tools to spin up 1,000 containers, run the feature extraction pipeline in those, and then get that data into a state where it's usable for ML. So one of our largest customers has, I think, 6 terabytes worth of labeled sensor data sitting in there, which they use to build these models. So we can deal with that, but yeah, our enterprise feature has a bunch of that stuff in.
Got it. So next question, how hard it is to connect a new development board to your platform? For example, new device board from ST.
Yeah, so the finalized model can virtually always run on device because we have the C++ library that we export has no external dependencies. It builds with a single make file, so really easy to integrate. So running the model on device, trivial, and then we load optimizations in depending on the dev board. To get data in, if you have data that's not at super high resolution, you can write the data over serial, and then we have a small data forwarder application that listens on your computer to get the data and forward it to us. But if you have higher resolution data, or you already have a way of getting the data off, maybe through an app, or you already have a cloud integration, just write it in the data acquisition format that we specify. It's very simple. Just what is the frequency, what are the sensors, and give me some sensor data, and then post it to the ingestion API, and it will just show up. So.
Okay, so do you have a documentation for that?
Yes, if you go to docs.edgeimpulse.com and they're getting started, and there's a porting guide as well that demonstrates all of this.
Okay, cool. So one of our attendees is asking, can we adapt Edge Impulse to teach kids, since it's an open source solution to a certain extent?
Yeah. Absolutely. We're running workshops quite often. Hopefully, if there's no travel bans in place, I'll be in Sweden in September to do a workshop with 50 people at the same time. It's super easy. If kids already have a mobile phone, then it's especially trivial to get started. And I think it's super cool for kids also to see that that machine learning is kind of a different way of programming, rather than I have a set of rules and then I have data come in, and then according to those rules, I'm going to make decisions. Rather, I have input and I have output, and now these rules need to be figured out automatically by the computer. It's still programming, but in a little bit different way. So if you can get kids excited about machine learning, and I think computer science in general through this, absolutely, please sign up. We'll do whatever we can to help. We can talk to our silicon vendors to sponsor some boards if needed. But I'd love to see more STEM and more education things on Edge Impulse.
That's awesome. Another question, can we build sensor fusion models with Edge Impulse? Yeah,
absolutely. So sensor fusion, the idea that you have 2 sensors, maybe audio as well as accelerometer data contributing to a single model, absolutely possible. So you can set up multiple DSP blocks that take data from different sensors, and then we'll fuse that automatically together in the final machine learning model. So we have a customer that's using PPG data, temperature data, and accelerometer data, all generating separate features and finally combining it into a single model that then runs conclusions over it. So sensor fusion is built in from scratch, built in from the start.
Okay. Thank you very much, Jan, for your great presentation. I guess we have to ramp up in a minute. So Jan's session concludes the first quarter of our virtual Tech Talk series. We focused on TinyML topics in the first quarter, since we just announced the new MCU and micro NPU M55 and U55 this year. Moving to the second quarter, we're going to switch our gears a little bit to cover other machine learning topics. On September 8th, where our very own ARM-NN team will present how to run accelerated machine learning applications on mobile and embedded devices. On September 22nd, our ecosystem partner Dory AI will introduce synthetic data. So we hope we can see you there. Another announcement. Yeah, so on October 6th to 8th, ARM's anchor event, ARM Dev Summit, will take place virtually. If you haven't got a chance to register, please use the URL here to register. So in the machine learning track, you will hear speakers from Google, TensorFlow Lite. Yeah, your OpenMV will be there as well. Facebook, PyTorch team, AWS, and other ecosystem partners. So if you want to test out Edge Impulse with the OpenMV camera, you can sign up Young's workshop, which will take place on October 8th, 11 a.m. Pacific time. Cool, thank you very much. And we hope to see you in our next session.
All right, thanks all.
Bye, thank you.